Well, now I will show you some practical examples of flange design. I will design a flange in accordance with clause 11 of the harmonized standard and then try to copy the same flange changing the method with the of Annex G instead of the method of clause 11. Well, let's start from an item for which we have already the cylindrical shell. First of all, the design standard. The design standard is EN 13445 Part 3, edition 2014, plus the amendments issue 5 of 2014, plus the amendments which were made in 2019. Then, let's look at the characteristics of this shell. This is made of carbon steel, P355GH EN 10028-2. The geometrical dimension are the length of 2 meters, a thickness of 15 millimeter, and an inside diameter of 1250 millimeters. The design conditions are 200 degrees design temperature, 40 bar design pressure, and a corrosion allowance of 1 millimeter. The joint efficiency is 1. Let's check the preliminary report of this shell. So we see that the minimum required thickness is 14.81. Therefore, it is logical to use 15 millimeter. One moment, there is let me check one thing. The under tolerance. We have forgotten the under tolerance because according to EN 13445, it is necessary always to take into account the under tolerance. So 0.3 millimeter, 0.3 millimeter is enough to lose the conformity with the standard. So 15 millimeter is not sufficient. We have to go to 16 millimeter just because of the under tolerance. So geometry, 16 millimeter is okay. And then we start from this shell and try to add a flange. Which kind of flange? An integral flange with hub, so a welding neck flange. Cylindrical shell left side, okay. Well, for this item we had selected already carbon steel material, so the material which was chosen by the software was P305GH 10222. It is a forging. Pay attention that when it has made the selection it has taken the lower thickness. Now we will see if this is adequate or not, but first of all we try to design this flange. So what we have to, all the characteristics, we want to have the characteristics automatically of the geometrical characteristics. So we have, however, to define something. So the bolt material is 25 chrome molybdenum 4, so it's a low alloy steel. We have to choose a gasket type. So a gasket type, we go into the gasket database. We will use a composite gasket made of flat metal, jacketed asbestos, iron or soft steel, and well, it's a normal gasket. I think we have better to select the gasket, at least the gasket width. The gasket width we will use 18 millimeter. According to TEMA, the minimum could be 13, but possibly due to the pressure and the diameter, I would recommend a higher width. However, we will see the consequences of this choice. We have also to select the minimum possible bolt, the minimum allowed bolt. So if this is a flange of a heat exchanger, the main flange of a heat exchanger, of course we have to consider the TEMA class. See, the TEMA class is R, So we have to select a bolt diameter, and nominal size, we look in the bolt database. There is a bolt database. The bolt database is metric because this was selected at the beginning, and so the minimum bolt diameter is M20 according to TEMA R. So number of bolts should be determined by the program according to the design procedure that I have already shown in the explanation. The gasket we have selected. Okay, let's see if it is possible to have a design just selecting the design mode here. And if we press on design, there is a confirmation that the design process will use TEMA M20 as minimum bolt. Do you want to proceed minimum because it's not assured that this flange can be designed with M20 bolt? I wish to proceed. Okay, the design is complete. Okay, so let's see which are the characteristics of this. Let me check one thing. The gasket that I selected 18 millimeter. Okay. If we go to our preliminary report, maybe we enlarge it a little bit to see this flange a little bit better. You see the profile of the flange. The profile of the flange is a flange with a very short hub. As I have explained before, the hub is, if you make a flange starting from a ring and not from a profile which has already a hub, the hub should be reduced to the minimum possible dimensions in order to minimize the cost. Bolt area, let me check how many bolts we have. Bolt load is here, hub stress, tangential stress, everything. Bolt type is TEMA M42. So M20 was not enough. It has increased all the dimension until it has found a size, a bolt size, which could be fit into this circle with this diameter. Of course, the E value, so the distance between bolt circle and outside diameter, and the R value, the distance between the bolt circle and the starting point of the hub, are the dimensions recommended by TEMA. Note this ISO TEMA bolts. What does it mean? Because bolts are ISO. But in TEMA, the characteristic of ISO bolts are slightly different from the characteristics normally used. So there is a little, the bolting area is a little bit less than usual. So since we have decided to be in accordance also with TEMA, this choice was necessary. So now there is a warning, a yellow warning. Let's check what is the yellow warning. The warning was exactly the material, because the material cannot be the class of material up to a thickness of 35 millimeter, because the total thickness is 135. So no problem, we go back to the database and we try to see which are the next P305GH. There is a forging up to from 50 to 106 millimeter. Okay, we choose this dimension, and now let's run again the design, because it's not assured that the thickness is the same. We go to general, we press again the design, we confirm the minimum 42 volts, okay, the minimum M42 as a bolt size, okay. The weight of this flange is 641 kilograms. So the number of bolts is always 44. the side 42 M42 was right, also changing the material, and we have already our flange designed. So if we want to see it a little bit, okay, this is the flange. This is the flange, it seems adequate. One thing, 44 bolts, there is a thumbs rule very old used by all designers that say that the number of bolts should be more or less the 1 bolt per inch of diameter. In this case, since the diameter is 1250 millimeter, 1250 millimeter means more or less 50 inches should be 50 inches, more or less, yes. And okay, we have 44 bolts, so it seems rather correct. One more thing, let me check where is the gasket. So again, preliminary report. Okay, the gasket has been placed at the lowest possible diameter. So the gasket is aligned with the inside diameter of the flange. We do not discuss this choice. This is certainly the best possible choice. And now we will try to see what happens if we use Annex G. So we confirm the flange, and then we will copy this flange to the other end of the shell. So copy welding neck flange 1. The most logical position is on the right side of this shell. Okay. Would you like to edit it now? Yes, I want to edit it now, because I just wanted to change the design rule. Note that there is not a design procedure with Annex G. So we have only to proceed by different trials in order to find if the flange is adequate or not. Okay, Annex G, and now we have to change, it's necessary to change something. Keep the geometrical dimension, but of course we have to change, for example, the gasket table, because the gasket table is not the same of clause 11. So non-metallic flat gasket, no, it is covered metal jacketed gasket, soft iron or steel. Okay, this is the gasket characteristics. These are the gasket characteristics that are in Annex G. What we have still, a minimum design city stress. Okay, this will all taken automatically. Mean gasket diameter, gasket width, gasket axial thickness uncompressed, say 4 millimeter, for example. This is needed. And then for the bolts, we have, okay, it has taken all the characteristics. Bolt axial length depends on the flange thickness, because the flange thickness, so the geometry here, is 152 millimeter. Net flange thickness at the weakest section, if this is constant, if the thickness is constant, we repeat here 152. So the bolt length should be 152 2 times, because note that the methods of Annex G applies not to a flange but to a flange connections. That means 2 flanges plus bolts plus gasket. So what happens if we have not another flange? Simply the software will assume that there is another flange exactly equal to this one in order to make the calculation. Therefore, for the bolt length, we have to use additional bolt load. Bolt axial length is here. The automatic calculation, Okay, it will automatically calculated by the program. Bolt-up tightening method, this is important. So we use the impact wrench, so the traditional device used in all tire workshop. Coefficient of friction between bolt and nut, the program says 0.2, okay, that's a good average value. The scatter value will be determined automatically. So, what it is, okay, then everything seems to be, except for one thing. Let's look at the yellow warning. Okay, the yellow warning is a logical warning. Only one flange has been defined. The calculation according to NextGen 411 has been performed considering two identical flanges. But now let's see which is the situation. So this means a flange calculating according to clause 11 is also good in case you use Annex G. Let's look at how Annex G explains the results. So the bolt diameter is the bolting up is 0.75, so this is the load ratio. So the ratio between the actual bolt load and the minimum required bolt load, the allowable bolt load. We have 0.92, so we are not very far. Maybe we could see if we take out 40, if we take out 4 bolts, if this is still verified. Let me check bolts here. Instead of 44, we make 40. No, with 40, you see, we go out. So it's not possible to change, to reduce the bolt number. So we leave 44. What it is possible to reduce? Maybe the flange thickness, because you see 0.76. So we go to the design the geometry of flanges. Instead of 152, we can make 145, for example. 145. Okay, let me check the preliminary report. 0.85, no big changes for bolt, but for flanges, yes, but we can go also a little bit further. For example, geometry 140 millimeter, 140, okay. Everything was already okay. In the preliminary report, I see 0.93. Note that there was a reduction of about 50 kilograms in the weight of the flange, the finished weight of the flange. Possibly the weight reduction for the starting ring was also something more. One could argue, okay, we have used for the bolts a tightening moment, the tightening device, which is the impact wrench, which is rather, I would say, a rough device, for which the scatter value are possibly high. What happens if we use a torque wrench? With the torque wrench, everything is still okay. There is no big change. If we use, on the contrary, a hydraulic tensioner, measuring of hydraulic pressure, you see, changing the bolt device or using a more precise bolt device, you get the possibility of reducing the number of bolts. So, because we have 0.7, so the flanges remain more or less the same thickness, but it is possible to reduce the number of bolts. So, by 4, or more possibly 36.85. Well, at this moment, if 36 volt M42 are possible, one would say, what can we do if we reduce the bolt size? Reducing the bolt size means to go here, bolt database, instead of taking M42, we take M39 with 36 bolts. You see 0.98, so this is still possible, but there is something more that can be done if we use a smaller bolt size, because if you look at the database, M36 bolt database, you see that for each bolt size we have the value of the bolt spacing, of course, the radial distance RH and the radial distance RR. So sorry, this is for hubbed flange, this is for loose flanges, and then the edge distance 44.5. What is the, so we could reduce something also in the size, so M42, you have 49 instead of 44.5, and 62 the radial distance RH instead of 58. So this means that we could reduce the bolt diameter by the bolt circle diameter by 8 millimeter. Let's try to see if this is possible. So we leave M39 and then we reduce, so geometry, we reduce the bolt circle by 8 millimeter minus 8 millimeter, 14.14. Okay, yellow warnings. No yellow warnings. Okay, so this flange is still possible, and we have seen that always in the bolt database we have seen that from M42 to M39 the edge distance can be reduced. Edge distance is here from 49 to 44.5. So 4.5, that means 9 millimeter plus the 8 millimeter that we have on the bolt circle. We can reduce the outside diameter of 17 millimeter. So flange, geometry of flange, diameter of the weakest section, outside diameter 17 millimeter, 1503. Check is okay. Look, now we have reduced also the dimension of the outside diameter, the dimension of the bolt circle. We have 574 kilograms, so the advantage in weight is something more, because the original weight of the flange, can you still reduce a little bit the thickness? Here there is a 0.87, so say for example 135 here, 135 here. Let's look at the bolt length. 272, yes, okay, that's reasonable. And then 0.94, okay, the total weight is 554 kilograms. If we make the comparison with the other flange, we have 640 kilograms. So we have taken out 90 kilograms from the finished weight. That means something more from the weight of the starting ring. However, please take into account that one of the big difference was the fact of using a hydraulic tensioner instead of an impact wrench. So we have used a device with a better control of the load, with less scatter value. Now, if you want to see the difference in the loads made by the two methods, let's first check not this one, we don't want the preliminary report, we want the complete report of this flange. So the complete report is here, and you can see that the flange moment, flange stress, bolt loads, this is the one which is important, which is the minimum bolt area plus actual bolt area divided by 2 times the allowable stress of the bolts. We get 6,500,000 Newton. Okay, this is what is calculated with the Taylor-Forge method, but now if you want to see the same report for the other flange, I want to see not the preliminary report, I want to see the complete report. What we can find here at the end: axial compliance, average gasket, external bending moment. Where are the loads? Require bolt loads. Okay. Bolting up, internal pressure, hydraulic test. You see that in bolting up you have 11 million Newton, almost more or less the double. It's clear that this is a load that can be applied using a hydraulic tensioner, so a device which has a good control of the load. You have seen that in case you would have used an impact wrench, so the rough device without a very good control of the torque, the number of bolts would have been increased. So the number of bolts given by clause 11 is justified. So you see that the method of NextGen can give a real advantage if the torque or the load, the bolt load, is controlled by a suitable device. Otherwise, probably there is not a big advantage in using NextGen instead of clause 11. Okay, thank you very much for your attention.